All right, so we're recording now. If you're talking, you may be heard. What we're focusing on this lesson, now that you have done your quiz, is we're going to look at how we can use what's called the sine rule to solve problems in non-right angle triangles. So everything that we have done so far has used the trigonometric ratios, so SOHCAHTOA, and that works for right angle triangles. We can also apply what we know about trigonometry to non-right angle triangles. This part I think is probably new for all of you, even though there might be a couple who have done non-right angle triangles, but I know in year 9 when we did extension mostly we just got to right angle trigonometry, we didn't get to non-right angle trigonometry. So the first thing that you have to know when you are working with non-right angle triangles is how to label your non-right angle triangles. So you've got this slip to glue into your summary journal rather than copying out what I've got here. But the short version is when we label a non-right angle triangle, I'm going to use capital letters and lowercase letters. The capital letters are always for the vertices. So vertices are the angles. And the lowercase letters are always for the side lengths. And when we put our labelling on there, the B's are always opposite each other. So the angle B is on the opposite side of the triangle to the side B. The angle A is on the opposite side of the triangle to the side A, and so on and so forth. All right? It doesn't have to be A, B and C. You can call it P, Q and R. You can call it R, S and T. Whatever letters you want to use, that is fine. But the normal standard that you'll see in most texts and online will be A, B and C. All right, so the next step is how do we then actually use this to find side lengths and angles in non-right angle triangles. And the first way that we're going to use this is what's called the sine rule, also known as the law of sines. But this is why I very clearly talked about the trigonometric ratios for right angle triangles. We try to call them ratios. SOHCAHTOA, sine is the opposite over the hypotenuse. They're a ratio. We're now going to talk about the sine rule. This is a mathematical equation. I'm going to really quickly do the proof for the sine rule. You don't need to write this. You don't need to memorize this. I just know that lots of people often say to me, but where does it actually come from, Mr. Boot? I want to show you where it comes from because it's relatively simple. Okay, let's just pretend that this is my non-right angle triangle. I'm going to label this side A. Where does little a go, Jack? The other side. And then B. Now, just to mix it up, I'm going to do it different to this one. Let's call it C and C, B and B. All right, it doesn't matter where you put your A's and B's. It's not like the left-hand side of the triangle, the right-hand side of the triangle, or anything like that. It's just you've got to get those opposites going on. Lowercase c and uppercase C often look the same, so I tend to exaggerate my uppercase C just to make it definitely look like an uppercase one. All right, so how does this work? The proof is really simple. If I put a little vertical line in there and went from C all the way down to here and created a right angle triangle, I could call this the height of my non-right angle triangle, couldn't I? All right. Now, if I work with the left-hand side of my diagram, I worked with just that part. I'm not sure if that's going to be big enough. Hopefully it is. That's the height. This length here is B, and this here is capital A, angle A. So if we used our trigonometric ratio, because this is a right angle triangle, the H is the opposite, B is the hypotenuse, so I could write that sine A equals the opposite over the hypotenuse, or H over B. And then if I rearrange this to get H by itself, I could multiply by B on the other side. And now we've got a rule for what H is equal to. Sweet, this is the proof, this is where it comes from. Grab the other side of my non-right angle triangle. This is angle B, this is still H, and this is now A. Same deal, it's sine, but B this time is equal to H over little a, multiply by the A on the other side, and we've got a rule for H. We've got two rules for H here. H doesn't change, H is always the same height, isn't it? So we then use our simultaneous equations, and I'm going to substitute this H in for this H. And then my rule becomes B sine A is equal to A sine B. So we've created a rule that's just got A's and B's in it now. We got rid of a letter. We've actually eliminated H from my equations. And then we do a little bit of rearranging. I'm going to divide both sides by sine A. And then I'm going to divide both sides by sine B as well. Why would I do that? Because they cancel out, and I'm left with B over sine B is equal to A over sine A, which is this part of the sine rule. Now we can do the same thing and just like split my triangle up this way, and I get the other parts of it as well. There is a video linked into the lesson slides if you want to go through that proof in more detail. You don't need to memorise it, you don't need to write it down, but it's basically just lining up what H is, finding H with two different sides of the non-right angle triangle, and then equating them. Either way, we get this rule. This is what's known as the sine rule. You should write this into your summary journal. You need to know this rule. Now, it's not often that we have a rule with two equal signs in it. Don't freak out. We're only ever going to use two parts at once. So we might use the A's, we might use A and C, or we might use B and C. We're not sure which ones we're going to use yet till we set up our problem. And in reality, I normally just kind of try and set it up so I only use A and B, but we'll get there. We can use this rule for non-right angle triangles when you have two pairs of an angle and a side. All right, so in this case, what I like to think about is I'm going to use the sine rule if I can create a butterfly, just because it's a nice little way of remembering how I do it. If I can create a butterfly, sine rule works. So here, this angle, this side, we've got an angle and a side, they match up, they're a pair. Here's one pair. This angle and this side, they're opposites, they are a pair. And then with a little bit of creative thinking and a set of antennae, I don't think they're actually called antenna on a butterfly, but I'm going to stick with that. I've been able to create a butterfly. Yeah? Got to use your imagination. But if I have a problem where I can create a butterfly, I can use the sine rule to solve this. Sorry? Okay, just thinking? All right, sweet. So how do we actually do it? We can, oh yeah, that's my slide. There's my butterfly and that problem. There's another example. So go back a step. We've got C and little c. We've got B and little b. We can create a butterfly there. I can use the sine rule. Okay, let's look at an example. We're going to do two examples, and you're going to have a go at a couple of questions. Same deal as usual. If you want to copy this one into your summary journal as your example, go for it. But hopefully after doing the exercise, you will add your own more complex examples that are relative to your needs. Okay, first question, am I finding a side or an angle? Side, excellent. So my first example is finding a side. Can I create a butterfly on this problem? In which case I know I can use the sine rule. Sweet. I can create a butterfly. There's my butterfly. Lovely little butterfly. All right. Now I'm going to move into part 2. I know I can use the sine rule, so I'm going to start by labelling the sides on my triangle. This is little c, so what do you think I'm going to call this angle? Big C. Makes sense. On my original example, I've got a capital B here, so let's stick with that. We're going to call this one capital B. What's this side down here? What am I going to call that? Little b. So we've got little c, capital B, and we've got little b, capital B. I'm going to use my sine rule. I worked that out with my butterfly, and I've got B's and C's. Which part of my rule am I going to use? I'm going to use a part that's got the B and the C, so I don't need that part. So write down your rule. B over sine B equals C over sine C. All right, now we're following the same steps as we did for right angle triangles. We drew our diagram, we labelled our sides, we chose our rule. What did we do after we selected the rule? Liam? We substitute, perfect. So I want B is 7 over capital B sine 35 equals little c. Do we know what it is? No, so we just leave it as the c. And angle C, sine 105. So once we substitute, we should only have one unknown. That's the thing that we're trying to find. I want to find out what C is. So I have to undo divide by sine 105. What's the opposite of dividing by sine 105 degrees? Multiplying by sine of 105 degrees. So we're using our solving equation skills here. We're going to take what we already had and we're going to multiply it by sine of 105 to get C. So we times both sides by sine 105. From there, break out your calculator. Make sure it's in degrees. And then we're going to type that out. And I'm in a funny mode here. Let's just change my... That's better. So, trig. Oh, I don't want trig yet. What am I talking about? I'm going to actually create a fraction. And I had 7 over sine... What do we have? 35? Times sine 105. Hit enter. Now my calculator's in exact mode, gives me something pretty funky. How do I get rid of that and get just like a nice decimal answer? 11.8. And we don't have units. We didn't know if it was centimetres. We don't have to go any further. Now, have a look at your diagram. Does 11.8 seem like a reasonable answer for C in that diagram? Yeah. I think so. One thing to note, the longest side will always be opposite the largest angle. So if that's 35 degrees and 7, we're expecting C to be larger than 7 because that angle is larger than 35. All right. If you got an answer like 78, you might go 78 seems a little bit wayward, right? Okay, I'm going to pause the video there. Can you have a go at the second example? Okay, so the first example that we saw is when we're finding a side length. We're going to have a look at a second example now, just like, oh, I was on the right slide already. Just like when we did right angle triangles, we could find side lengths. We could also find angles. When we're using the sine rule, we can find side lengths or we can find angles. Let's work through this second example on the board and then you can have a go at one yourself. Okay, so when we did trigonometric ratios, right angle triangles, first step I told you was always draw the diagram. So let's draw it out. We had a B, 63, 5.5 and 4.7, and it wants us to find B. And it says angle B. So are we finding a side length or are we finding an angle? We're finding an angle. So example 2 is finding an angle. Okay, can I use the sine rule? How do I find out if I can use the sine rule? I need to be able to draw a lovely little butterfly. Can I draw a butterfly? Do I have two pairs of opposite sides and angles? So there's an angle and a side that are opposite each other. There's an angle and a side that are opposite each other. Have I made a butterfly? Yes, absolutely, we can use the sine rule. So let's move forwards, let's label our sides. This one's already B, so let's call this one little b. Haven't got anything for these ones. Oh, actually I have got a C down here, so let's use C and little c. We've got B and C. Which part of the sine rule are we using? We're going to use this part again because we haven't got anything about A's. We don't need to use A's. We're just going to use B and C. So write down the rule. B over sine B equals C over sine C. Substitute in our numbers. So side B is 4.7. Angle B, we don't know. Side C is 5.5. Angle C is 63. So this time my equation looks a fair bit different to before. My unknown is on the bottom line and it's also tucked inside these brackets next to sine. So we're trying to get B by itself. We're trying to work out what B is. When I solve these problems, like in the first example, it was really easy when I could just multiply. So I'm going to actually, my first trick here is I'm going to just flip both my fractions. I'm going to actually write this sine B over 4.7 and sine 63 over 5.5. I'm allowed to do this, all right? I can just flip them. Second thing I'm going to do, I'm trying to get B by itself, so I want to get rid of this divide by 4.7. How do I get rid of a divide by 4.7? Beautiful. We multiply by 4.7. So the sine B will still be here, and we'll have the sine 63 over 5.5, and it's multiplied by 4.7. We could type this into our calculator at this stage, but I don't, because what you tend to do is get a decimal answer and then make a rounding error. So I'm going to do it all in one step on my calculator. Last step, I'm finding an angle. When we did right angle trigonometry, what did I need to use to find an angle? The inverses, good. So we've got to do the opposite of sine. The opposite of sine is inverse sine. So when I want to get rid of this sine next to the b, I have to use inverse sine. Sine to the -1. Okay, so to get b, I'm going to do inverse sine of everything that I already had. So it looks like a really ugly equation, but you're not expected to do it by hand. All I want you to do is break out your calculator. Okay, so trig, inverse sine, use the fraction template to help you. Make it look right, because then you're less likely to make a mistake. Sine 63 over 5.5 times, be nice if it was a touch screen, it's not, times, what was my other number, 4.7. And then I hit enter, and my calculator's automatically given me a decimal this time. We get 49.58. I'm actually going to round off to the nearest whole number, because often we do with angles, and it will be 50 degrees. And if you want, you can keep your little squiggly equal sign in there to indicate that this is approximate and that you have rounded off. Okay, finding an angle, we'll always use an inverse sine, or an inverse cos, or an inverse tan, depending on whether you're working with a right angle triangle or a non-right angle triangle. Okay, can you have a go please at this one? And I'll pause the video.